Hi. How was the lunch today? Good? Better than yesterday, right? So let's establish some ground rules. If at any time during this talk you think, I don't understand what this guy is talking about, just try to get my attention and ask your question right there, because it's probably a sign that I didn't explain something well enough. My name is Wietse Venema. I'm an engineer in the Cloud Run team at Google. I'm based out of Amsterdam, which means that I don't have a sense of humor. And I really like birds. So what's the talk about? It's about two things, right? I'm going to show you how to build and deploy an application that uses an open large language model. That's Act 1, right? And then Act 2 is I'll show you how to provide tools and give the LLM autonomy to decide what to do. And if that doesn't sound exciting, let's get started with a live demo. So I have a very simple demo app. It will get more complicated later. So I can send a query to Gemma, which is an open large language model, and I can see the response. So let's start with one. Okay, I didn't know it would turn into a poetry recital, but let's take a look. Okay. On Flanders' shore, where diamonds gleam, Antwerp stands, a vibrant dream. Cobbled streets and history's call, a portrait, nice, I like port call, a portrait embracing all. Thank you. I was like, it started to feel a bit awkward, but thank you. I have one fan in the audience. That's good to know. If you think I'm making a joke, it's okay to laugh, right? Loosen up a bit. Well, to build the app, right, I use the following components. There's Google's Gemma 2, which is an open large language model. There's Ollama, which is an LLM inference server. I used LangChain, which is an LLM integration framework in Python. I don't like Python much. I'm a recovering Java programmer. I usually write Go, but hey, Python it is today. And Gradio, which is a framework to rapidly prototype machine learning demos. And this is what my architecture looks like. It's not too complicated, but let's dive in. And let's start with Gemma. So Google's Gemma is an open large language model. And what does that even mean? Open means that you can download the model weights, right? The learned parameters of the neural network. It's not the same as open source, right? Because that would mean that we open up all the training data and how we trained it. That's not the case. Open models are models where you can download the model weights. And there are a few actually open source models out there, but not many. Now those model weights, here's an example for Gemma 2 with 9 billion parameters. They come in a set of very large files, right? At full precision, which is 32-bit floats, they weigh, for Gemma 2 with 9 billion parameters, it weighs 38 gigabytes in total. So that's a lot, right? Imagine trying to run inference on that. But there's quantization. So that's a way to take a very large model and produce smaller and faster models out of it. And what it does, it will reduce the weight's precision to improve the memory footprint, because all those weights have to be loaded onto the memory of your GPU, and also improve the inference speed. And then it becomes much better, because if you take all those 32-bit floats and you quantize them down to 4-bit integers, the model size is just 5 gigabytes, a little over 5 gigabytes. So that's a lot more manageable. It does make the model less accurate, but surprisingly enough, it's often minimal, right? So I suggest to run inference with 4-bit ints, and it's even better if the model is originally trained for 4-bit, because it provides a good balance between speed and accuracy, and you can optionally perform use case specific tests with larger model weights. Now, for Google's Gemma, there's 5 different variants. So there's Gemma 2, that's the one that wrote the little poem for me. It can do other things, like spelling words backwards. Oh, that didn't work quite well. miraculous. It should be Sua Lucarim. So there's 5 different variants. I'm going to fix that later, don't worry. There's 5 different variants. There's also Code Gemma, which is a model that you can use to generate code and code completions. Poly Gemma, an open vision language model. Recurrent Gemma, which uses recurrent neural networks instead of transformers. And there's Data Gemma, which aims to reduce hallucinations by connecting with Google's data commons. In my demo, I use Gemma 2, and later I will also use Code Gemma, but that's for Act 2, so you don't have to worry about that yet. Okay, so you have the model weights. Now you want to send prompts to this open model, so you need an LLM inference server and a GPU, because otherwise it will be very slow. And there are many options to choose from. There's Hugging Face TGI, Torch Serve, Ray, VLLM, Llama.cpp. I'm not sure what the llamas have to do with this, but there's Llama.cpp and Ollama. And that's the one I picked. And it uses Llama.cpp as the engine. And why did I pick it? Because it has a really nice mascot. No, it's a user-friendly and performant LLM inference server. So there is a desktop app with a command line client, so you can do offline inference on your Mac or whatever laptop you have. It comes with a REST API and an OpenAI compatible endpoint. And it supports many open models. I will show a selection later. And they make it very easy to download the model files, so you don't have to go to the Hugging Face hub and download the model files and then quantize them down manually. They already done that for you, so you can just say, well, let's do Gemma to 9 billion parameters, quantize to 8-bit, and run inference on it. It's a bit like, it feels a bit like Docker, right? You actually, it looks a lot like Docker, and no surprise because the founder worked at Docker. So I can Ollama pool. So I installed, you can see the little llama there, Ollama pool Gemma 2, and then I will wait for minutes while 5 GB downloads. No, it's already here. So, but if my demos work, I need a bit of validation. Like, thank you, thank you. Let's send a query. Maybe that works too. Ollama run Gemma 2. So this will take the model weights and load them on the video memory of my GPU. And then I can start sending queries to it. Right, boom. Thank you. Look, you got me. I like this. You can do booing as well if it doesn't work. Or like, let's loosen up a bit. Write a poem for me. Should I recite this as well? Or that was too awkward, right? That was too awkward. It worked yesterday. Okay, so that's Ollama. You have an LLM on your MacBook. Don't need to use the cloud or anything. And the token speed is pretty awesome. Like, write a poem, tick, 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 tick. It goes faster than I can read. So that's good. Open models, reasons to like them. There are many of them. Like for specific use cases, I ordered them by downloads, and while it's great that there is a bunch of models from Google there, there's a lot of alternatives there. The ubiquitous Llama from Meta, Nomic embed text specialized for embeddings. There even is one, it's very small, you can read it, but there's Reader LM, and you give it HTML, raw HTML you crawled, and you get back Markdown. They trained it for that purpose, right? So this open model community is really great for innovation because people take those open models and they retrain them specifically for other tasks. And I think that's amazing. Like, it's better than only having proprietary APIs. So for fast inference speed, a GPU is required. So, and what I like about Ollama is that it will detect what GPU do you have, how much video RAM is there, how much of the model can I fit onto the GPU, and maybe I have to run a few layers in the CPU. It will figure that out and set sensible defaults for you. If you were to use the Llama.cpp engine that's underneath, you would have to configure that manually. And yes, it can run inference on a CPU, but only the very small models will run fast enough. Likely if you do a 2 billion parameter model, your CPU will be warm, maybe even hot, but it will have a fast token speed. But less parameters means lower quality. Yes, and the available video RAM of a GPU limits the size of the model you can load, right? So you take the number of parameters, more or less multiply them by the number by their precision, and then you get how much video RAM you need to load the model and run inference with an acceptable token speed. And Ollama runs great on Cloud Run, but more about that later. I'm in Team Cloud Run, so. Okay, so back to my app. LangChain is an LLM integration framework in Python. And here's how it works. Sending a prompt to Ollama using LangChain. I start with initializing an Ollama client, give it a name of the model, temperature setting, and then I create a chat prompt template. So this is where you fill in the input. And then I set up a pipeline, a chain, right? So the chain is, you start with the input gets filled into the query placeholder in the prompt template, then it sends the prompt to the model, in this case Ollama, through the REST API, and the last step is to output a string. And then you got something that you can invoke, right? So why is the sky blue? That's the hello world of LLM apps. So that's easy. And because LangChain provides this abstraction, I can change chat Ollama for a different LLM implementation. It has the same interface, so my code doesn't change. My prompts, that's the secret of LLMs, right? The code might not be changing, but the prompts do, because they're tightly coupled usually to the model. Change the model, and suddenly the results are wildly different. And then there's Gradio, which is a tool to rapidly prototype machine learning demos. And they are of the form, I have input on the left-hand side and output on the right-hand side. So it's all in Python. No need to embarrass myself with my HTML and CSS skills. So you configure an interface component. You set the function to call to handle to handle the input. So in this case, it's my little bit of LangChain code that you just saw. And then you define declaratively the UI components. So you can have just one text box as a query, but you can add other input forms. And then the output, in my case, is a markdown file. That's a weird word to use. It's a markdown panel. And then you serve the thing. By default, I set share to false because I don't want to create an SSH tunnel to have this ngrok-like thing to get a public link. I listen to all network interfaces, and I started on a specific port. Now, what's great about this app is that it doesn't need internet to run, right? And that's pretty cool, I think. I have 3 reasons. Maybe you can come up with more, but there's 3 reasons why I think that's great. So all the data you put into it stays local. It's yours. It's under your control. You're not sending it up to a proprietary API, and then, well, their terms said that they wouldn't do anything with it. So, but this makes it very visible that it's in your control. I like that. And you have full control over model upgrades. If you don't want to touch this app for the next 10 years, I likely won't touch this demo app for the next 10 years, but it will still run. And I'm not forced to migrate to a new version. And it's portable to any hosting environment, right? I like Google. They pay my salary. Maybe in 5 years, I don't like them anymore, and I want to still run my app somewhere else. So that's where open models really win. But today, I deployed my app to Cloud Run on Google Cloud. And so I created a Cloud Run service for my Ollama server, which is GPU enabled, because I want to have fast inference speed. And there is the second service, which is my front end, and that has the Python app with my Gradio app. Now, who's familiar with Cloud Run? Anyone? 3, 4, 5, 6? Okay, I will quickly take you through what is Cloud Run. I think it's the easiest and fastest way to deploy a web application on Google Cloud. And here's why. If you create a Cloud Run service, you give it a container image, or maybe if you don't want to write Docker files, you give it your code. And then you get an HTTPS endpoint back. No need to configure servers or load balancers or anything. That's like the key thing of Cloud Run. And it has auto-scaling built in, right? So a service auto-scales in real time to respond to incoming requests. That means we start one container instance. If it gets very busy, we add another one, and it scales down. It even scales down to 0 if there are no incoming requests, which is very cost effective. Now, Cloud Run supports, we launched this at the end of August this year, supports GPU in preview. So you get one NVIDIA L4 GPU, and the type of GPU is important here, right? Remember, video RAM is important. So our L4 GPUs have 24 gigabytes of VRAM. So it means that you can easily load 2 9 billion parameter models on the video memory. And maybe I didn't try, but maybe I could even load the 8-bit quantized versions of it without issues. So you get one GPU per container instance, and you can have many instances per service because it's auto-scaling. And it still scales to 0 if there are no incoming requests. And I like that for my demo because I don't want to pay full-time for the GPU. I do have to confess that before I got on stage, I configured minimum instances, so it wouldn't scale down to 0 because I don't want to, like, it will be fast, right? Because processes in a new container instance, they can access a GPU in approximately 5 seconds, but then I still have to, which is fast, right? Ever tried booting a VM? So we engineered this to be really fast, or I say we, the engineering team did that. And I still need to wait for the model weights to be loaded onto the video memory. So that would mean that we would have to wait 15 seconds before I could start reciting the poem. Another thing that's great about Cloud Run is that container images are imported into Cloud Run. So it's not pulling them from a remote registry every time you need to start a new instance, but they are imported into Cloud Run's infrastructure in a way that we can materialize them very fast. We even start the entry point of the container before the container image is there. Like we mount a remote file system and it streams the data while it's starting. And this is really great for those large model files. Put the 5 gigabyte file inside of the container and then it will be materialized very fast. And it scales out very fast. So during the launch event in August, we showed a service that generates images with stable diffusion. And it scaled to 100 GPU instances in under 4 minutes. And that was very expensive. But you can set limits, right? So I said, for my demo, I set my maximum instances to 3. So that's more than enough. Okay. To prove that I'm not joking about this, I will show you my services deployed. This is the Google Cloud Web Console. I'm in Cloud Run here, and there's 3 services. So here's my GPU-enabled service. And I configured it to have request concurrency of 4. I'll come back to that later, but it's important, especially when serving LLM inference workloads. Maximum instances is 3. 4 CPUs, 16 gigabyte of RAM. That's the minimum you have to enable before you can enable a GPU, and 1 NVIDIA L4 per instance. Now, and this instance is not accessible by the outside, right? It has a public URL, but if I send requests to it, let me show that. I will get a forbidden error back. And that's because I set it to require authentication with Cloud IAM. So that's how you do internal services in Cloud Run. There's another more difficult way. I won't show it today because this is easier. Yes. Okay, about request concurrency. This is important for LLM inference apps. So Cloud Run lets you, or you have to, limit the request concurrency per instance. And there's one reason why that is really great for LLM inference. It's because LLM inference speed quickly degrades when handling concurrent requests on a single instance. So you go to 4 concurrent requests, 5, still good speed, and then you add more, and then suddenly it becomes very hard for your GPU to keep serving all those requests. LLM inference is very hard to parallelize. And that's why most LLM inference servers, I think all of them, have built-in concurrency limits for this reason, right? So if you send more concurrent requests to a server instance, it will start queuing them on the instance itself in the inference server. So Ollama has an environment variable, Ollama num parallel. Hugging Face TGI has a flag, maximum concurrent requests. And a good limit is likely much lower than you think. Like, remember how this worked with connection pooling and databases? It's always way lower than you think. But my connection pool has 1,000 instances and it's still very slow. Okay, for GPUs, concurrency is even harder. So Ollama, for example, defaults to 4, and they do this by pipelining. My recommendation is to run tests with a variety of prompts so you can get a feel and determine the right limit. Now, Cloud Run lets you limit request concurrency per instance. And it also uses it for autoscaling. And that's great, because if it were to look at utilization, the chances are that you would send more concurrent requests to one instance than this inference server can handle. And what happens? You get queuing on the instances. And that's not good, right? So because request concurrency limiting is built into Cloud Run, queuing on the instance won't happen, and Cloud Run will add instances. So your inference speed stays good. Okay, so my front-end service is public. The Ollama service is internal only, and this is how I did it. So the Ollama service requires IAM authentication to make it internal. And that means that if you send a request, you need to add a valid OIDC token to it. So that's a JSON Web Token. And it should refer to a service account that has the run.invoker IAM permission on the service. And as a sender, you create this token using a client library. So because my sender is also a Cloud Run service, it will be pretty straightforward. Okay, it's time for Act 2. I did show you how to build and deploy an application that uses an open large language model, and I hope you now have a pretty good idea of what settings you need to tweak to make sure that it performs well and it scales well. But it wasn't good, right? It made a bunch of errors because I just sent one prompt, and well, that's great for demos, writing a poem, but we want more, right? So I'm going to show you how to provide tools and give the LLM autonomy to decide what to do. And in true Silicon Valley idiom, this is how to build an agentic system. I like how they come up with new terms, and then everyone wonders, agentic, that sounds interesting. Like, it has agency. I still don't know what agency means, but it is interesting. It has to be interesting, right? It sparks your intellectual curiosity. But this is how to provide tools and give the LLM autonomy to decide what to do. So I already hinted at the limits of my demo. It cannot spell words backwards, and it also doesn't know what day it is today. And it's also very bad at counting. Let's try one. What is the sum? All numbers from 1 to 10. I think it's 55. Might be in the training data. It's in the training data. So you think it has this ability, but in reality, it can't. Maybe? You don't know. If you're a good calculator, tell me if this is right or not. I don't know. So there's limitations. What do we do to fix them? You can use a few strategies, right, to improve the quality you get from just one prompt. You can then dynamically add relevant information to answer the query in the prompt itself. That's retrieval augmented generation. I think that's another Silicon Valley trope, really. Retrieval augmented generation sounds very agentic. So next step is create linear change, right? You start with, hey, can you answer this query? And then you send another query. Maybe you can reflect on this answer. Is it right or not? Can you give me ways to improve it? And then you send a third prompt with the feedback. So you got this feedback on the answer. Can you improve the answer? So you can improve quality by bit using that strategy. You can use routing. So based on this query, maybe handle this type of query in a different way than the other. I'll show an example. So that's already adding a bit of agency, a bit of autonomy to the LLM, because it will decide what path to take. And you can provide tools. So to solve my problem, I can provide a function to reverse strings. I can in my prompt, I can tell the LLM, hey, you can call this function to reverse strings if it's useful to you. And then it will respond with, sure, I want to call your function. And then you prompt it again with the answer. Like that's tool calling. But maybe I can come up with something more extensible and exciting. So I decided to use code Gemma to write and execute code to answer my queries. So this is my agentic workflow with tools that provides autonomy. So first, I get my query, spell the word miraculous backwards, and I prompt my model, hey, do you want to write code to answer and execute code to answer this question, or just answer it? Decide, please. Now, if it decides to write code, I will give this same query to code Gemma, which is an open large language model that can write code for me. So it will do that, and then I will use a tool. I will execute the code that it generated for me, and that's my response. And the other path is just answering the query. Demo time. So, can you spell the word miraculous backwards? Okay, sure, I'll perform several steps to answer the query. First, prompt Gemma to decide what to do. It chose to write and execute code, because it can be done using Python string slicing and reversed. Then I prompt code Gemma to generate code, which looks correct. There's no reversed function though. And here's the correct answer, suo lucarim, which everyone knows is the reverse of miraculous. And it also knows what date it is today. Shouldn't come as a surprise. And today is Thursday, October 10. I can do even more exciting things now. Who's familiar with this orange site? Quite a few people are. Okay, so this, if you're in Silicon Valley and you're a hacker, you go to this orange site to post links to things that spark your intellectual curiosity. And then you'll get a lot of comments that are sometimes very technical and often opinionated. Like, I don't know if you got the thread about HTMX a little while ago. Like, that was brutal. Okay, so there's an API. So I can prompt my little demo thing. Like, hey, there is an API you can call. And this is how you retrieve an item. Here's an example. And there's another call that lets you return a list of all the front page stories. Now tell me, what is the title of the highest ranking story? It decides to write code because, well, it's a problem you can solve with code. Then it generates some code. And there's the answer. And it is correct. You're my new friend, thank you. I like that. Again, like one of the slides in my presentation I created with that, like the one that has all the open models, there is no way to like figure out all the models that are in the registry. So I wrote a similar prompt, giving it like, this is the, if I have time left at the end, I will show you. So this is the web page. All the model names are in this div in a table. Give me all the names, and it worked first try. So. Okay, but what doesn't it work? Maybe I can ask it to recite a poem again. Oh no! To answer this query, I choose to write and execute code. I wonder what it comes up with. Oh, a nice comment. Good find. Define different sentences, then print one. and then history. This is nice. I like it. It's like the output is still good, but I'm not sure if I like how it got there. Thanks. Right. So that brings me to the next point. Right. Well, this prompt. How do you do the first step? So I give it the query, and I give it this prompt. This is what I came up with, and I think I can still improve it because, well, it gets it wrong sometimes. I say identify user queries that are best answered by writing and executing simple Python code, And please only use built-in functions and models, because I don't want to do pip install. I don't even know what models to use, right? And I shot a few examples, and I ask it to return a JSON object because I need to render my response in the markdown panel. But this is the hardest thing to get right? This routing. So I've like the example that just came on screen. I have another one here. It made a list of random poetry lines and then printed them randomly. So that's the thing. If you're building agents, providing more autonomy will make like the results sometimes like it takes the wrong exit somewhere in your chain, and it will be a really bad result. So I'm not sure how you should improve it. Maybe exposing this to the user in your application works, right? So they can debug it for themselves, or like it really depends. But this is really hard. Okay, so the simple path was just answer the query. Well, you can guess what this prompt is. Answer the question clear and concisely. And the other part starts with writing code using code Gemma. So code Gemma is this Gemma variant that's optimized for code generation tasks. And the one I used was natural language to code chat. So I prompted like, hey, write code that answers this query if you execute it. And there's two other variants that are for code completion. One is higher quality, the other is very fast. And this is the query I give it. So write code that when executed prints the answer to the query. Only use built-in functions and modules. Start with putting the input in the variable. Was important because otherwise it would generate a function for me to call, and I wouldn't know what input to provide. And format the response in such a way that it makes a bit more sense instead of just printing the answer. And then finally, execute the untrusted code in the sandbox. And well, I say untrusted code because if this were an application for a user, they would start to try and figure out the boundaries of my code execution environment, right? I think there was this thread on Twitter, and someone found a way to extract the OpenAI key from a system that also used code execution. So you really have to be careful with this. Now, Cloud Run can also be a great sandbox for running untrusted code. You can restrict Google Cloud API access from instances using IAM, because every Cloud Run instance has a service account attached. You can create a service account specifically for that service and do not provide it any permissions. So that's how you can wall that up. You can prevent concurrent access, so two queries cannot interfere with each other, setting maximum concurrency to 1. You can prevent access to the VPC network. So you can enable it, but by default, there's no access to the VPC network at all, so it runs in isolation. And there are a few features that also help. So instances on Cloud Run are ephemeral, and you cannot address them individually. So that limits a lot of the possible attack factors. By the way, if you want to have like persistent state on Cloud Run, you can totally do that, because you can store state on a shared file system or in a database, right? But the instances themselves are ephemeral. They can disappear at any moment, if they're not serving a request, of course. And there's another feature that also is great. Like, you cannot start a background process. I mean, you can start a background process, but CPU speed is strongly limited on instances that are not handling requests. And that's because the default pricing model of Cloud Run is to charge you only for instances that are handling requests. Now, this is something that you can turn off if you don't like it, but the default pricing model is really pay for use, only for instances that are handling requests. So if they're idle, if they're not handling requests, you don't pay for them, and that's why we limit the CPU speed. So it will still be running, but it will get a lot of less cycles, CPU cycles. Okay, so that's the complete workflow from query to response. I used LangGraph by LangChain to orchestrate this. Well, it isn't really complex, but I'm sure it can be used for complex workflows. And it looks like this, right? So you start with initializing a workflow, and then you add different nodes to the graph. So this router node is my function that does the prompt. Hey, Gemma, can you decide what to do? Write code or provide an answer? Coder node is also a function that is prompting code Gemma to write the code. The execution node, it doesn't make any prompts. It will take the code. So all those nodes, they have access to a shared state object that you can refer to, and the output is added to the state. So we'll take the code, which is the output of the earlier node, and then we'll execute that in the sandbox service. And then there's a general node, just answer the thing. I set the entry point, and then I start to connect all the nodes. So you add edges. From what state does it end? And there's one conditional edge. So I have another function, choose agent, that will look at the output of that first decision node and then decide what's the next node, what I do now. And then you call compile on this, and you get a function that you can invoke, just like the chain in my first demo. So that's great. LangGraph is super helpful here. Now the summary of this is like you can use Ollama and open models to build offline first LLM workflows. You can build agentic systems to make LLM apps more useful by providing tools and giving the LLM more autonomy. But it is hard. So the rewards will be large, but it is really hard. There's Cloud Run with GPUs, which offers scale to zero GPUs without the infrastructure complexity. It can also be a sandbox for running untrusted code. And LangGraph is super useful to help orchestrate complex LLM workflows. And now you can ask any questions you want. Or none at all. I see one hand.
The sandbox mode, does it prevent like code that is like generates a lot of requests to hack any news?
Yeah, so you want to. No, you need to build. Yeah, that's it. It
can be like it can.
Sure.
DDoS.
Yeah, so you would need to limit outbound connections if you want that. Yeah. So you can route all the outbound requests to through a proxy. Okay. There is a secure web tunnel thing on Google Cloud that you can use and then rate limit outbound requests and the domains they can access, for example. And there's more things, like you also need to think of like, oh sure, I can time out the thing, but what if it starts a background process? Maybe I want to kill the instance every time. So that's something we're exploring, like, hey, maybe we want to add a platform feature to support that. Because anything you try on the instance is hijackable from the generated code, of course. And you can do some sanity checks on the input, so yeah. But there are dragons hidden, so be careful. Any other questions? I see another hand. Yeah.
So how much is the cost of keep that instance running at the minimum level possible, for example, for 1 hour?
For 1 hour? I don't know the number off the top of my head. It's not as cheap as CPUs. And also, with CPUs, you can enable this request-based pricing, and then you pay like 10% of the list price for idle instances. But for GPUs, we don't do that. So the answer is look it up in the pricing. But you can schedule the minimum instances as well. So if you this is where I do the minimum instances. I can schedule it to only start one during the working day. But hey, the cold start is still pretty fast. So maybe if you don't mind that people have to wait for 10 seconds, it's fine to not do it. The lights make it hard to see hands. Yes.
You're generating code or choosing to write a function.
Yeah.
And the interaction with the actual inference engine, that's stateless. But
yes.
Does the function's life cycle last past the point of the user input? Like, what's the life cycle of the functions that are getting built? So user asks a question.
Yeah.
You go through the loop. I'm going to write myself some code, and and then that code gets used through that loop.
Yeah.
And then the user's finished. When another person comes and asks a question, do the previous functions remain, or does it constantly
So in this case, I said there's two components, right? There's the front end that has a high concurrency, so it can handle more than one thing at the same time, more than one request at the same time. So it depends a bit on what part it is running. But handling the one user query is one request, right? For the front end part. And there can be many running at the same time, and it keeps running. It doesn't act. Like there is no default that stops an instance after it handles one request.
I meant the tools that are getting generated.
Mm-hmm.
It was choosing to write some Python code and then use that to answer the question.
Yeah, I call out to another service that does only the sandboxed execution of the code.
The code that got generated and then they got used as a tool.
Yeah.
Is that tool still available when some other person makes a call to ask a question?
No, but that's an interesting idea. Like, no.
It seems it's quite an inefficient way of generating code.
Yeah.
So but if it remembered them and slowly built up a toolbox.
Yeah, like caching for generated code. Yeah,
Yeah.
I like that idea. This could be a fun experiment to do. Like, cool. Yeah. Great question. More hands. Yes.
So you deployed the Ollama container?
Yes,
Was it auto-aware of the GPUs, or did you
Yeah.
have to enable some settings?
No. So I used the Ollama. I actually wrote the tutorial on this. There it is, Ollama Cloud Run. So I take the Ollama. I'll zoom in a bit. I take the Ollama Docker container, and it knows to, like, it has CUDA, and also on Cloud Run we auto inject all the CUDA libraries, so you don't have to install them yourself. And here's the thing I do. I during building the container, I pull in the model weights from the registry, so they are in the container image for fast startup. Any more questions? I'm easygoing. No questions are bad. Or I don't do the booing. It feels like there's a question coming. No? Not that tingling sensation? Like, okay. No, okay. Well, then I guess you're free to go. Like,
All systems are nominal. Initialize Genesis sequence.